In this video, we're going to talk about the fundamental solution set. Okay, so we're talking about linear homogeneous systems of ODEs. So recall, we've seen that the set of solutions to a linear homogeneous system of ODEs, so something that looked like x prime equaled a times x, where A is an n by n matrix, this set of solutions is n-dimensional, which means we should be able to find n linearly independent solutions to this. Okay, so that fact is going to tie into this next theorem. So this next theorem says, well, if we can find those n linearly independent solutions, and if we call them x1 up to xn, to our system, so x prime equals a times x, then we can write down the general solution. So the general solution should have the form, I'll call it x vector of t. It's a vector valued function. It's going to be all the linear combinations of these n linearly independent solutions. So it'll look like c1 times x1 of t plus dot 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 up to cn times xn of t, where the c1 dot 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 up to cn are real numbers. So that's what the general solution will look like. Okay, so in this case, we say that the set of these n linearly independent solutions, x1 up to xn, we call this a fundamental solution set for our system of ODEs, for our linear system of ODEs. X prime equals a times x. And we call, so sometimes we take those n linearly independent solutions, x1 up to xn, and we put them into a matrix as the columns. So if I call that matrix X, this is called the fundamental matrix for this system of differential equations. X prime equals a times x. So this is just a little bit of terminology. So fundamental solution set, that's our set of those n linearly independent solutions, written in set notation. And if we put those n linearly independent solutions as columns in a matrix, that matrix is called a fundamental matrix. Okay, so the next key question is, now that we've talked about all of this, we haven't really answered the question, well, how do we solve our system of, our linear homogeneous system of ODEs? And the answer is, we are going to use eigenvalues and eigenvectors. And this is the topic of sections 9.5 and 9.6, which we will start in the following video. But we've seen, a flavor for why this is, why it uses eigenvalues and eigenvectors, because we did that in the motivating example, the very first video in these two sections, 9.1 and 9.4. Okay, so what I want to end this video now is just briefly by talking about, well, so far we've looked at the homogeneous case. Well, what would the solution to the non-homogeneous case look like? So recall that the non-homogeneous case, the equation looks like the following. I have x prime of t equals a of t times x of t plus, and there might be this other vector valued function, f of t. So f of t, actually for it to be non-homogeneous, there needs to be this f of t. And this needs to not be the zero vector. When it's not the zero vector, that makes it non-homogeneous. So the key idea to solving a non-homogeneous system like this is going to parallel what we saw with matrix equations and when we had a non-homogeneous matrix equation. So the key idea is, if xp is a particular solution to this non-homogeneous equation, which means if we plug it in, it satisfies it. So xp prime of t is equal to a of t times xp of t plus f of t. Okay, then a general solution to our non-homogeneous equation will be x of t. So I'll call it x of t, and x of t will be the sum of the particular solution, xp, and the homogeneous solution, the general homogeneous solution, which I'll call xh. So xh, this is the general homogeneous solution. And at this point, we know what form this will have. This will look like C1 times x1 of t plus dot 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 plus Cn times xn of t, where the x1 up to xn, they are n linearly independent solutions to the homogeneous equation. So this parallels what we saw with matrix equations and what the solution to a non-homogeneous matrix equation looked like.